Socratic math tutor here. So for this particular question, we're given a point x comma y in the plane. And this point actually depends on a parameter t. So this is a parameter. And so as t varies, we trace out a curve in the plane. Now for part A, we're actually not focusing in on the entire curve. We're just going to look at this line. So y equals something dependent on t. And unfortunately, the difficulty of this question depends sensitively on how you actually read it. So there's sort of two readings of it, and one kind of makes the question easy and one kind of makes it hard. So let's talk that out a little bit. Here on this first line, we've got dy dt squared equals this. So let's just write that down. And then down here, it says, show that a, b, and c are these three numbers. So it seems that we're trying to use this to show that a equals 1, b equals -2, and c equals 16. Now the problem with that reading of the question is that this direction is actually quite tricky. And I mean, it's not super hard, but I think it really involves techniques that go beyond the scope of the specialist math course. So for example, one approach for doing this involves row reducing a 3x4 matrix. And if you do that properly and you invoke the right theorems, you can get this conclusion popping out the end. But I honestly don't think that that's what they meant by this question. And there's a few reasons I say that. So one of the main reasons is that you're only given 4 lines to do this, to do part A. And it's only worth 2 marks. So it's not worth a lot of marks. There's only 4 lines available. You're not going to have space there to apply any of these techniques that actually solve the problem. And as far as I can tell, these techniques seem to go beyond what's actually taught in specialist math. So that's one reason I think this forward direction is probably not what's meant. The other reason is that according to the examiner's report, this question was quite well answered. And I just don't think that would have happened if they were talking about the forward direction. So therefore, my interpretation of what the question is meant to say is that what it's really trying to say is actually the backwards direction. And the backwards direction is really a lot easier. So all we do is we take these numbers, we stick them in here, put them in place of A, B, and C, and then we just check that this equation with those changes is actually true. So that's a lot easier to check, and that's what I'm going to do in this video, because I think that's what they genuinely meant. Now, if you have any reason to believe that I'm wrong about that, please comment, and if you can convince me that actually they meant the harder direction, I'll delete the video and I'll rebuild it from scratch. Okay, so let's go ahead and try and show that this is true. So show this line. And so we'll do this just by computing dy dt and then squaring it at the end. So dy dt equals, we look here, we've got y equals log to the base e of something. And so the derivative of that is that something in a denominator with the numerator replaced by its derivative. So in this case 1, plus 1/4 times the same thing. So I put the 1 minus t in the denominator. I put the derivative of 1 minus t in the numerator, so that would be -1. And of course, because we like to just skip steps, we'll get rid of that, and we'll get rid of that line there. And the way I see it, we might as well make this a single fraction line. We'll get some brackets going down here, extend that over, and we'll put a 1 there. Okay, now we're trying to show that dy dt squared has this form. So we need to square both sides of this equation. And on the right-hand side, we have a difference of 2 numbers. So think of that as a minus b. And we're going to square this difference. And so we need to use the formula a minus b squared equals a squared minus 2ab plus b squared. So let's go ahead and apply that up here. We've got dy dt squared equals the first term squared. We're going to do plus the second term squared at the end. And you can see this is sort of lining up with what we were targeting. And in the middle, we've got this minus 2ab. So I'm going to write minus 2 over, and we're multiplying these terms together. we might as well just focus on the denominators. We need to multiply the denominators. And so I'll just actually just write the product of those denominators right there. And so that makes it clear to the reader sort of what the step was. You know, we haven't done too much in one step to make sure that the reader is following and to make sure that the examiner actually knows that we've justified our steps properly, because, you know, notice how similar what we've got already is to the target line. If we just jump straight to the answer, there wouldn't be any evidence there that we actually understand what we're doing, right? Okay, so let's rewrite the first part. So 1 over 1 plus t in brackets squared. We'll rewrite the last part. So 1 over 16, 1 minus t squared. And then we'll just go ahead and simplify this expression. So we cancel a factor of 2 from both the top and the bottom. In the numerator, we get 1. In the denominator, we get 2. And we also need to multiply out these brackets, right? And so using difference of perfect squares, the product of those brackets is 1 minus t squared. So at this point, we've nearly got our target expression, right? So the first bits are the same, the last bits are the same. The only difference is here we have a plus versus here we have a minus, because up here, the negative is actually in the denominator. So I sort of feel like we can probably just make that change right there. And so my thinking is, okay, we've written down 4 lines. We were given 4 lines to solve the problem. This is probably full marks. And I think the lesson here is really that you need to keep in mind the amount of marks available and the amount of space you've been given. So if the literal question being asked is way harder than what makes sense in light of that information, it might be worth just reinterpreting the question so that you can actually do it in the allotted space, and so that its difficulty makes sense in light of the allotted marks. Okay, so we're ready to go on with part B. I haven't actually erased everything that was on the screen. I want to keep this insight that if dy dt equals this expression, then the square of dy dt equals this expression. And the reason is because to solve problem B, we need a trick, and that trick is suggested by this computation. So I'm actually just going to summarize it at the top of the screen. And so I've got that basic insight here. And as we go through part B, we'll see that this expression actually gives us the trick that ultimately solves the problem. Okay, so for part B, we're trying to find the arc length, and they're calling it S, of the curve from t equals 0 to t equals a half. So let's go ahead and write that using some notation. We have the arc length from t equals 0 to a half of x of t, comma y of t. And hopefully you know the formula for this, and it's actually on the cheat sheet, so there's no reason you shouldn't be able to write this down. We integrate between our two endpoints, and we need to integrate the square root of dx over dt squared plus dy over dt squared dt. Okay, so this is the integral from 0 through to a half of, okay, big square root sign. Let's give ourselves lots of space. Put dt at the end so we don't forget it. For the first part, we need to find dx dt. Now, x is arc sine of t, and so that means dx dt is actually 1 over the square root of 1 minus t squared. And we actually need a dx dt squared here, so we need to square that. And just to save a bit of time, I'll just put that in, the simplified form straight away. And so now we just need to put in dy dt squared, which, as you'll recall, is this thing up here. It's pretty much given to us, in question A, because they give us these numbers. And so basically we just need to put this stuff in here. We can go ahead and simplify a little bit. So in particular, you'll notice that we've got a 1 minus t squared here. We've got a 1 minus t squared here. And so that affords us some opportunities for simplifying. So I'm going to actually rewrite this term as the first term because there's no simplifications available there. I'll rewrite the last term as the last term. Again, nothing to simplify there. And for this middle bit, we've got a minus a half here. For this 1 over 1 minus t squared, we implicitly have a 1 here. And so we've just got to compute 1 minus a half, which is positive a half. And so what that tells us is that the coefficient of 1 over 1 minus t squared here needs to be 1/2. So you can put it in like that, and then just combine them with plus. I'll extend that out. I'll put a dt at the end. And at this point, you're probably thinking, wow, that looks like a really hard integral. Like, how in the world, is there some kind of trick? Can I let u equal 1 plus t or 1 minus t squared? Is there some special u that solves this? Well, actually, to solve this, what you need to do is notice that this expression inside the square root here really looks a lot like what we had up here, right? The only difference between this part and this bit in the square root is that here we have a -2 and here we have a +2. But that's literally the only difference. And so the only thing that controls that difference is actually the sign of this. Okay, so if we think of this as a plus or minus, well, we get a plus or minus here. And in particular, we're interested in the plus case here. I mean, for part A, we were interested in the minus case, but now we've flipped. We're looking at a different expression, and we just happen to be looking at the plus case. And so what you can do is you can say this is the integral from 0 through to a half of the square root of basically this thing all squared, right? Okay, let's make a bit more space for ourselves, so we can get rid of all that. Put this up high. We'll go ahead and call that S, just for clarity a bit, because they've called it S here. And it should be pretty clear that this is the integral from 0 to a half of the absolute value of this stuff in here. And it turns out that we actually don't need the absolute value signs here. Okay, so get rid of those, put some brackets in, and let's just spend a moment understanding why it is that we don't need the absolute value sign. So the reason basically is that over the interval of interest, right, so we're just going from t equals 0 to a half, and over that interval, this expression is positive, and so is this expression. And so therefore their sum is positive, and so we don't need the absolute value sign for that reason. Now, if that's not clear, I think the best way to proceed is probably just to draw some graphs. Okay, so here I'll graph 1 plus t. Here I'm going to graph 1 minus t. So 1 plus t looks like this. 1 minus t looks like this. We're interested in this interval from 0 through to a half. And you can see here in both cases that these numbers are positive. So 1 plus t is positive over this interval, and therefore so is the reciprocal. So this expression is positive. And 1 minus t is positive over this interval, and so therefore so too is the reciprocal, which is this part. And then obviously multiplying that by 1/4 will still result in a positive number. And so that's why this whole expression is always positive, and that's why we don't need the absolute value sign. Okay, so let's finish off the problem. We learned that S equals, so it's the antiderivative of 1 over 1 plus t, which is log to the base e of 1 plus t. Put our terminals at the end, plus 1/4 times the antiderivative of this, which is actually negative log of 1 minus t. Put our terminals at the end. And notice that sticking in t equals 0 into these expressions always gives us 0, right? So for example, if I put t equals 0 here, I get 1 plus 0 inside the brackets, which is 1, and so log to the base e of 1 is always 0. And so therefore we're getting 0 in the t equals 0 case. And the same thing happens over here. So therefore we can just focus in on the t equals a half case. I'll put t equals a half into here. We get log to the base e of 1 plus a half, which is 3 over 2, minus 1/4 times, put t equals a half in here. We get log to the base e of 1 minus a half is a half. And this is almost in the form that they want. They want log of something plus, a fraction times log of something else. The only catch is that they've actually got a plus here and we've got a minus. So just to be safe and just to make sure that we get those marks, I think it's better to just put a plus in. So plus -1/4 times log to the base e of 1/2. Now the way I see it, this question is finished, so this deserves full marks in my view. But based on the examiner's report, we should go one step further. So I'll just rewrite the first bit, plus 1/4 here. And what we basically need to do, we need to take this negative out here and put it in as an exponent. And so we're raising 1/2 to the power of -1. And that just flips the fraction. Okay, so technically both of these are in the form that they're looking for. But this gets an extra tick because it's even simpler. So that's the arc length of the curve from t = 0 to t = 1/2. And hopefully that should get you full marks for this particular question.